Hello, statistics students. Today we're going to learn one of the most important and fundamental theorems in all of statistics, and that is the Central Limit Theorem. This is a biggie. So let's dive right in. We're going to talk about sampling distributions and how they relate to the Central Limit Theorem. When we first learned what a distribution was, we said a distribution was a table that showed what values a variable took on and how often it took on those variables. Then we graphed some of those distributions. We liked histograms because it took, frequency histograms gave us what values our variable took on, and then the height of the rectangles was the frequency telling us how often our variable took on each of those values. What we're going to do today is talk about sampling distributions, and then the graphs of those sampling distributions are going to lead us into the Central Limit Theorem. So let's get started on a sampling distribution. Imagine that you have a population that's approximately normally distributed, has a mean of mu and a standard dev of sigma. Now, I'm going to take a sample of size little n. I'm sorry, that's not normally distributed. That means a population of size big N. It's early in the morning. So, and notice as I said sample normally distributed down here, it does not have to be normally distributed. So I'm glad I made that correction. So it has a sample size of big N, or nu, a mean of mu, and a standard dev of sigma. We're going to take a sample of size little n. So imagine you got millions and millions here. We're going to take a sample of size 10, for instance. And I'm going to take the average of that sample. That's my first sample, so that's x1 bar. I'm going to take a second sample, also of size n, and that's going to be x2 bar. I'm going to take a whole ton of samples of size n. In fact, let's just say that I could, if it were possible, take every possible sample of size little n. So in other words, how many different samples would I have? I'd have big N choose little n of these different samples, and I'd take the average of all of them. And let's say I graphed all of these averages. The new graph of all those x bars is what's called the sampling distribution. Let's do it one more time. If you were writing, put your pencil down and listen. Say you have a huge population of size n, big N, mean of mu, standard dev of sigma. I'm going to take a sample of size little n, some small sample. Could be a big sample, but let's make it small relative to this number. I'm going to take the average of that sample, and that'll be x1 bar. I'm going to take a whole ton of these samples, all of them of the same size, n, and I'm going to get all these x bars. In fact, if I could do that, the true sampling distribution is actually if I were to take every possible sample of size little n and average it. If I graph all these x bars on, say, a frequency histogram, for instance, that new graph would be my sampling distribution, sometimes called the sampling distribution of the sample mean, because we're graphing all these means. So that is the sampling distribution. Before we go on, let's think of this. Let's say I graph all of these. Would you think of it this way? The bigger your sample size is, the bigger n is. Wouldn't you imagine that you'd get less variation in these? If you took a sample size of 3, yeah, you're going to get some variation. But if you took a sample size of 20, do you think these averages of each of those samples of size 20, you think that graph is going to be spread out? is the graph of the sample size of 3. Because I mean, if you have 20 samples, I mean, if you get a big one over here, you know, if you got 20 data points in your sample, you're probably going to get a small one over here, and it's going to average pretty close to the middle. You're going to get a bunch on either side of the middle, and they're going to average out. I mean, you know, if you have 3, you could get 2 over here and 1 over here, or 2 over here and 1 over here. I mean, that average can move around a bit, but with 20, the average isn't going to move around a lot. And that's extremely important concept for the central limit theorem. Now, when some people, I will ask you to memorize the central limit theorem. Just start memorizing it. Not word for word, of course, but the idea. Some people only want to memorize what's in black. That's not good enough. You need this part too. And the central limit theorem says this: stop writing. You can pause whenever you want and write. Listen to me. Take any population. Doesn't have to be normally distributed. It could be some crazy distribution with a mean of mu and a standard dev of sigma. So you just calculate the mean and standard dev of that distribution. Now, if it's not normally distributed, 68% of the data will not fall necessarily within one standard dev of the mean, because that empirical rule only applies to normally distributed data. But you can still calculate the standard dev. So, given a population with a mean of mu and a standard dev of sigma, if n is big enough, and we'll talk about what that means, but in any case, as long as n is at least 30, n is at least 30, this pretty much always holds true. Okay, so here's this part here is kind of our introduction. Given any population with mean of mu and standard dev sigma, if n is big enough, or in any case greater than or equal to 30, then 3 things happen. First, your sampling distribution will be approximately normal. The mean of those x bars, in other words, the mean of your sampling distribution, will equal the mean of the population. And the standard dev of those x bars, how spread out those x bars are when you graph your sampling distribution, will be this sigma divided by the square root of n. What that means, and it goes back to what I said a little earlier, the bigger and bigger and bigger n gets, you remember when I compared the sample size of 20 to the sample size of 3? The bigger n gets, the less variation you have in those x bars, and your normally distributed sampling distribution gets skinnier and skinnier, and of course taller. So again, if you have a population with a mean of mu and a standard dev of sigma, and if n is big enough, then the sampling distribution will be approximately normal with a mean of mu and a standard dev of sigma over root n. Here's what that means. Let's take a population. Let's just say I'm just going to simplify it a bit. And let's say our population is normally distributed with a mean of mu and a standard dev of sigma. Well, if I take a sample of 16 from this, I take 16 data points from here and I average them. 16 data points, average them. 16 data points, average them. And I plot all of those, then I'm going to get a sampling distribution that's approximately normal. The mean of these x bars, the mean of the sampling distribution, will be the same mu, but you'll notice that it's taller and narrower now. It's going to be sigma over 4. So you see that the variation here is only 1/4 of the variation of the population. Because when you have 16 data points, if you get a big one, you're probably going to get a small one. And even if you don't, you're going to get enough down here that average, it's going to pull this in towards the average more. The average will not be as spread out as the data are. So your sampling distribution has the same mean as the population, but the standard dev is the standard dev of the population divided by the square root of n. So how do you know when to go with sigma as your standard dev or sigma over root n? Whenever you take a sample and average it, you're working with a sampling distribution, and hence you need to work with the sampling distribution. I'm sorry, you need to work with the central limit theorem. So since this is the beauty of the central limit theorem, is the sampling distribution is going to come out approximately normal, which means we can use z-scores. Now, the z-score, the way we write it is a little different, but it's doing the same thing. Instead of an x data point, remember the things you graphed are really x bars now. It's an average of one sample of size n. So it's x bar now. And the mean is the mean of the x bars. And the standard dev is the standard dev of the x bars. So it's still a data point minus a mean all over a standard dev. The difference is now that we know that the mean of the x bars from the central limit theorem is sigma, and the standard dev of the x bars, how spread out that sampling distribution is the population sigma over the square root of n. So when we write a z-score using the central limit theorem, oftentimes, I mean, why write sigma x bar and mu x bar and sigma x bar? Why not just write it like this? And the z-score is still telling us the same thing. It's telling us how many standard devs away from, or how many standard devs away from the population mean our sample mean is. If we pick one sample and one sample from that sampling distribution. Also, the sigma over root n, and you'll see it often referred to as the standard error. Again, error in statistics does not mean you've made a mistake. It just means variation. So let's talk now with an example problem of how we can utilize this. So we're going to do an example. We're going to go to Costco, and Costco advertises that this car battery they sell has an average of 5,000 starts with a standard dev of 300. And they tell us that, we ask, and they tell us that distribution is pretty normal. Okay. Well, let's say I work for Consumer Reports magazine and I want to evaluate this. How many batteries do I have to test to see if this is true? Well, I'd have to test, I think the scientific number is a crap ton. So I'm going to make use of the central limit theorem. I'm going to test 10 batteries. And what I got from those 10 was a sample, an average of 4,900. Should I believe Costco? You say, well, no, your sample is less. Well, yeah, that's a sample. We know samples can vary, low or high. I mean, samples aren't always going to be exactly on, but what I want to know is, let's say I could possibly sample every, if we had all the Costco batteries out there, I take every sample of size 10 that there were, and I tested them and I were to graph that, that would be my sampling distribution. Now I want to ask, what is the probability that I'd get 4,900, and I'm going to give you a little secret here. We want to go, what is the likelihood of getting the results I got or something more extreme, if this is true? Now, if it's pretty likely that I would get a sample of this, given that this is true, then I don't have any evidence against this. if it's pretty unlikely that I'd get a sample of this, given that this is true, then I'd say, it's possible I just got a fluky sample, but I'm more likely to believe that this is wrong, that my sampling is okay and this is wrong. So let's calculate the numbers. And remember, when we say, well, how likely is it? There's no hard and fast rule. But in stats, unless you're given information to the contrary in a problem, we're pretty much going to stick with 5%. If there's more than a 5% chance of something happening, we're going to say that's pretty likely. If there's less than a 5% or 5% or less, we're going to say that's unlikely. So according to the central limit theorem, my sampling distribution should have a mean of 5,000 and a standard dev of approximately 95. Now that means that all those samples of size 10, if I could take them, would give me this sampling distribution. So each data point here is actually an average, represents the sample average from a size of 10. So here's 95, here's 4905. I got a sample of 4,900. So remember, the probability of getting exactly 4,900 is what? 0, because this is a continuous distribution. But I want to know the likelihood of getting the results I got or something more extreme. And if I'm going less than, more extreme means to the left. So what's the probability that I got this result or something more extreme given these conditions in blue? So I convert this X bar is less than 4,900. I've stated the problem in terms of X bar actually, but you get the idea. I calculate my Z-score, X bar minus minus mu all over sigma over root n. This becomes a Z-score, well, this is -1. This turns out to be -1.05. So I'm 1.05 standard devs below the mean. How likely is that to happen? Well, I'm looking at the area under the curve to the left of -1.05. So the area under the curve is just the table value, and it's this. So there's over a 14% chance that even if this is true, that I would get a sample that had, my sample of 10 batteries would have an average of only 4,900 starts. So I don't have any evidence right now, or I don't have strong evidence at all to say that Costco's statement is wrong. So that's our introduction to a sampling distribution and the central limit theorem. You've written it all down. Let's review. A sampling distribution is what you get when you take every possible sample of size little n out of a population of big N, and you average them. Now you don't have to average, but that's mostly what we're going to do. You average those samples and you graph them. That's the sampling distribution. And the central limit theorem says if you take that population that has a mean of mu and a standard dev of sigma, in other words, here's our population. If your sample size is big enough, or in any case greater than or equal to 30, 30 will always be big enough, then the sampling distribution will have three things you can count on. One, it will be approximately normal. Two, it will have the same mean as the population does. And three, the standard dev of the sampling distribution will be the standard dev of the population divided by the square root of the sample size. Again, this is one of the primary, fundamental, primo important rules in all of statistics. So it is important that you get this. You notice I got a little note here for page 263. And in class, I have an applet where I can show you in practice what this means. So that's all I have for now. Have a great day.